let's talk about power. Power, this is a pretty easy concept to add to our list because power is the rate at which energy is transferred. In or out of a system. I think that in or out of a system isn't really necessary, but in or out of a system. I mean, you have an object or something, you know, and you're going to do work on it, and the rate at which you do work is what we mean by power. And we'll use a capital P to represent it. Now, the rate at which energy is transferred, well, I'm going to call that like a change in energy, right? A delta E. That is, energy has been added or taken away from a system. So I'll call that delta E for change in energy. And then divided by the time it took to do that. And now this delta E, you know, you have to look at the problem you've got. You know, like if you've got a pot of water on the stove and you're adding heat to it, it's the rate at which you add heat. Now, heat is measured in calories, but it cannot be measured in joules, right? And then you just divide it by, you take the energy that you added to that pot of water to make it boil or whatever, and you divide it by the time it took to do that. Or if you're pushing on a cart, you know, it took time to accelerate that cart, okay, down the track or something like that. So you just take the work that you did on it and divide it by the time it took to do that work. So anytime there's an energy transfer, whether it's heating or work or, you know, there's various ways, and if you read that section, they talked about some other ways of transferring energy. You know, electrical current can transfer energy, and so on. So however you're moving energy in or out of a system, that change in energy, just divide it by the time, and you've got what's called average power. This, when you have deltas, we usually call it an average because it's kind of stretched out over a period of time, over a time interval. Now let's look at the units here. Energy in the metric system that we use is measured in joules, and time is measured in seconds. And so a joule per second is called a watt. So we have a new unit here, but I think you've heard of this one, right? A watt. Like, how many watts does that speaker put out? You know, like 50-watt speakers, 100-watt speakers. How many of you are like into, anybody in here into sound systems? Okay, no. Used to be a big deal. Now everybody's got iPods and stuff. And those speakers don't put out a lot of power, because if they did, they'd blow your eardrums out. But, you know, when I was growing up, a way of trying to make yourself better than other people was to have really powerful speakers, you know, like, you know, 50 watts, 100-watt speakers. And, or maybe greater or lesser. I didn't really know because I wasn't as cool as them. But a watt is a measure of power. And we abbreviate a watt with a W, which is kind of unfortunate, right? Because what also starts with W? I mean, what work? I mean, we use work to represent, a W to represent work, and now we're using W to represent watt. But you have to look at the context. Like, this is a unit. It's not a variable. So when you see like a number like 27 W's, That doesn't mean 27 work, all right? It means 27 watts. So if you just look at the context, it's pretty easy to figure out. Okay, so now this is, because of the deltas here, this is called average power. But I think if, you know, I think you know what we're going to do. Now we're going to talk about instantaneous power, the rate at which you're transferring energy at an instant in time. Okay? It's kind of like velocity, right? We had average velocity. It's the rate at which we're changing our position. If we average it out over, like stretch it out over a time interval, you had, you know, delta R over delta T, and we called that average velocity. But then we said, no, just let delta T, take the limit as delta T shrinks to 0, and, you know, take the derivative, and you get instantaneous velocity. Well, that's what we're going to do here. This is average power, but if you want instantaneous power, all you have to do is take the limit as delta T goes to 0 of your change in energy over change in time, and of course you get dE dt. Okay, so you can express it as a derivative, no problem. And again, this using this E for energy, this is pretty flexible. I mean, if you look in the book, they start off talking about work, the rate at which work. I like to generalize beyond what the book did, because there's more than one way to transfer energy, right? You can transfer energy through heating, radiation, lots of different ways of moving energy from one system in or out of a system. So I'm just going to use E for energy. Now, but if we did use work, I mean, look, one way of transferring energy is, well, we said that, you know, if I have work, thank you. If I have, you know, what my definition for work, right, was F dot dr, right? That's the most general form, and I've got an R initial and an R final. I'm just too lazy to write it down. Okay, but what if I take this little integral sign away and say, no, let's not sum them up yet. Let's just look at the force times a little tiny displacement. What do I get when I take the integral sign away? What happens? Well, this turns into a differential, right, form. And really what we get is a little tiny bit of work, d work, is equal to F dot dr. Do you agree with that, right? Think about the little rectangles that you draw under the, right? 'Cause, I mean, when we explain integration to people, here's force and here's some R, you know, and we have a, you know, how do we find the area underneath the graph, right? We divide it into zillions of little rectangles, and then we say, okay, here's a little rectangle, and we give it a little width of dr, and it has a height, you know, this is F of R, okay, at that R, and we multiply them together and get the area. Now it's a tiny area, it's infinitely tiny. I didn't draw it infinitely tiny because you can't, all right? But you see what I'm saying? So this is a little tiny bit of work done. So what I can do is take that little tiny bit of work done and divide it by a little tiny bit of time that it took to do that work, and I can get the instantaneous power. Just divide both sides by dt, I get dw dt. Now this is not a watt, this is work, so we're talking about work here, is equal to F dot dr over dt. That makes sense? Heck yeah, algebra lets me do that. I have not violated any mathematical laws here. Well, this is kind of interesting. What's dr dt? That's velocity. So I can say that power is the rate at which I do work, and that can also be thought of as the force that's doing the work dotted with the velocity vector. Now here's this is a dot product, right? This is, I mean, the scalar product. Power is a scalar. You wouldn't say, oh, my toaster uses 300 watts to the north. Okay, your toaster doesn't care what direction. I don't know, like, how would that work? Okay, so power is one of those quantities where direction is not a part of it, so it's a scalar. But we use two vectors to figure it out. So if you know what the force is and you know what the velocity is at that time, you just take the dot product, and that's the rate at which work is being done on that object by that force. Yes?
Oh, okay. So you were saying that like power is just basically like any kind of energy over time, right?
It's the rate at which energy is being transferred over time.
Okay.
I mean, energy has to be moving in and out of your system, whatever your system is. You know, my system could be like, you know, my good old cart on wheels, right? My crate. We love crates. I love them. Okay, so here's a force, right? And that force is going to move through some displacement, delta x. Okay, so it's doing work as it's going through here. But if I want to say, okay, how much work from here to here, and then I divide it by the time it takes to go from here to here, then I've got the average power. But if I want the instantaneous power, then I've got to do this. Now, one thing, let's say that this is increasing in velocity. Maybe it has initial velocity like this, but then when it gets over here, you know, whew, it's going so fast. Look, it's swooshing. Maybe it's going a lot faster. Think about this. This force, if you go force times velocity over here, the power is less than it is if you apply that same, maybe it's a constant force. If I apply the force times this velocity, it's much greater. Well, yeah, think about it. If you're going to push on a cart and you're going to keep that acceleration going, you're running a lot faster. And to keep that force going, you've got to put out a lot more energy in the per unit time over here than over here. So it really does make a lot of sense. Okay, so power is again measured in watts, and you can use you know, this power equals dE over dt. Now, so power equals the rate at which you use energy, the rate at which you're transferring energy. Now, I'm going to rearrange this formula a little bit because you'll get problems like this quite often. And what if I multiplied both sides by dt here? I get a little bit of energy is equal to power times a little bit of time. Okay? Now, by the way, notice how I am saying these equations out loud. Okay? I don't say P equals dE dt. No, I try, well, sometimes I do. But I try to say power equals, you know, the change in energy over the change in time. I mean, I try to say what the quantities are. Like a little bit of energy, well, dE, that's as little bit of energy as you can get, right? It's an infinitesimal amount of energy, is equal to power times a little bit of time, a little infinitesimal bit of time. So, what if I wanted to know how much total energy has been transferred? Well, integrate both sides. And you get delta E is equal to the integral of P dt. So power, maybe power is a function of time. Maybe it's constant. I don't know. Times dt. I'm sorry? Tiffany. Yeah, go ahead. Borrow Tiffany. Okay. So now, if power is a constant, if you have a constant power, you'll have problems where the power is going to be constant. That makes this problem really easy because here you have the energy transferred will be equal to, well, the power comes out of the integral, right? And what's the sum of all the little dt's? That's delta t. So this is just going to be power times delta t, which kind of gets me back to my original definition here. I've just rearranged here. Now, this makes sense. Let's take a look at units here. This is in watts times seconds. This is the unit watt. Maybe I'll write it out because you guys are just getting used to this. So watts times seconds. Well, what is a watt? So a watt is a joule per second times a second, right? So this will cancel and you get joules. So the units make sense. But let me show you one last thing before we are done here. PG&E, or whatever power company you have, they don't sell you power, by the way. People use the word power and the word energy interchangeably in everyday life, which is fine because everybody knows what you're talking about. But in physics, we have to be precise in our language. You don't buy power, you buy energy. Power is the rate at which you're using that energy, and so the more powerful all your all your refrigerator and your air conditioning, the more powerful those things are, and the more you use them, the greater the amount of energy you've used. And so they need a unit of energy. You buy a unit of energy. Now, joules are a joule of energy. Basically, pick up a small apple and lift it over your head. That's about a joule of energy, maybe even a little bit more. That might be a couple of joules of energy. So that's a tiny amount of energy compared to what all the appliances in your house are using. So they don't use joules. Well, one thing they ought to use is megajoules, because a megajoule, that's about what you would use, and I mean, a megajoule is a good unit of energy for utilities to use, but they don't use that. They use a funky little unit for energy. It's based on this. Okay, the energy unit that they use. Well, for power, they use kilowatts. Now, kilo in the metric system, right, is 1,000. That's 1,000 watts. And then times time, they use hours. So what they charge you for are these units of energy that are expressed in units of power and time. A kilowatt hour. Have you heard of kilowatt hours? All right. A kilowatt hour. So it's thank you. A kilowatt hour. Quite often you see it written that way. Kilowatt hour. So it's pretty easy to figure out. Now I think on my power bill, which it should be called an energy bill, but they call it a power bill. It's stupid. Okay, sorry. An energy bill. It might cost you 20 cents or 30 cents a kilowatt hour for electricity. Okay. And so, but how many watts? I mean, how many joules in a kilowatt hour? That's pretty easy. So 1 kilowatt hour. Okay, put it over 1. We're going to get rid of the kilowatts. 1 kilowatt is 1,000 watts. And then 1 hour is 3,600 seconds. So 1,000 times that, we're dealing with millions here. So that goes away, and this goes away. So 1 kilowatt hour is equal to 3,600,000 joules, right? Wait a minute, what did I do wrong here? And
6 times 1, and then you have to add 5 zeros, so that makes sense.
yeah, but I didn't end up with joule. Oh, I know what I needed to do. A watt is a joule per second, so that'll cancel out the seconds, and then you get joules. Now this is 3.6 megajoules. 3.6 megajoules is a kilowatt hour, which is, I say, well, why don't you just use megajoules? But because first of all, megajoules is pretty cool to say. All right, sounds like something from Transformers. Ooh. All right, and but I guess it's pretty cool to say kilowatt hour. I mean, that sounds pretty vicious too. So, all right. So this should give you what you need. Oh, there is a weird unit of power that has been used, and I don't really know the origins of it. Like in the American customary unit system, that's really stupid. We have these things called horsepower.
Oh, okay.
Right? Have you heard of horsepower? Well, actually, horsepower is now defined based on the metric system. Like the inch, 1 inch is defined to be exactly 2.54 centimeters.
Oh, really?
Yeah. That's the definition of an inch.
It's not actually like some kind of infinite, like irrational numbers.
No, it's 2.54 0 0 0 0 0 with a little bar over the zeros, okay? And so really our system is based on the metric system in this weird way. The horsepower is defined to be 1 horsepower is equal to 746 watts.
Exactly.
I think that's exact, yeah.
Like 746.0000.
I you know what? I'm being recorded here, so I don't want to. All right, so that's it. Good luck, and go out there and have a powerful day.